Chapter 7.2, Volume by the disk method. Today, the volume of a solid with known cross-sections. What's different about today is we're no longer going to be taking this region here, whatever that is, and rotating it. Okay? We're not doing that today. Today, what we're going to do is we're going to take this figure there, what it is, and we're going to build on top of it. And we're going to build in such a way that there's going to be shapes on top, such as you could have squares up top. We could have rectangles up top. We could even have semicircles or triangles on top. So we're going to build with known cross sections: squares, semicircles, rectangles, triangles. It's going to kind of look like this. All right. Here we have a little shape. Here's the base of our shape down there. And you can see on this one, we're building squares that are perpendicular to the y-axis. So this one's going to be done with respect to y, dy, because we're perpendicular to the y-axis. Over here, this one, we're building trapezoids perpendicular to the x-axis, so this one will be dx. All right? And it's pretty much the same thing. When we rotated, every cross section ended up being a circle, so our integration ended up being pi radius squared the circle dx or dy based on what we were perpendicular for. Well, today it's going to be the area of a square times dx, integrate that. Or the area of a triangle, dy, integrate that. All right? So it's the same thing, we're just using areas of different shapes to find our volumes. We're going to look at one example today, and we'll just do a little bit more examples tomorrow. Today, just get your feet wet and see kind of what it's like. So we're going to integrate here. We got this shape, which is built upon this region of the graph using equilateral triangles. So we're going to need to figure out what the area of an equilateral triangle is, and because we're building like that, we need to figure out what the area of an equilateral triangle is in terms of the base. All right? So our area needs to have just one variable in it, not base and height. So as we look at it, here's our equilateral triangle. Here's our base. There's our height. Now normally our area is, of course, 1/2 base times height. But we need to get rid of this height here. All right? Well, if you remember an equilateral triangle and you split it in half, you get what's called a 30, 60, 90 triangle. Where this ends up is also a representation for our base. And then this side, to get the short leg, you divide the hypotenuse by 2. And to get the long leg, if you remember the magic number is the square root of 3, you take the short leg times the square root of 3 to get the long leg. The short leg is base over 2, so base square root of 3 over 2 is our height. We substitute that in. Our area of an equilateral triangle is 1/2 the base times the square root of 3 over 2 times the base, which will clean up and be square root of 3 over 4 times the base squared. So as we're building this shape over here, with our equilateral triangles on this base, we're going to integrate. Since we're perpendicular to the x-axis, we're going to go with respect to x. Our x values go from 0 to 2. And square root of 3 over 4 times the base squared is our volume or our area formula. Square root of 3 over 4, like pi, is a constant, so I'm going to pull that out front. And then our base, which has to be squared, I'm going to need a little bit more space, I think. Our base, which has to be squared, is this line right here, which goes from this function down to this function. So we're going to take the top, 1 minus x over 2, minus the bottom, which is -1 plus x over 2. Okay, and we can clean that up. We got here, we'll distribute the negative sign. Got 1 minus x over 2 minus a negative is plus 1, minus a positive is minus x over 2 squared dx. Combine like terms. Right now it's just algebra. That is where most of mistakes usually happen in calculus, is doing the algebra. So that's 2 minus x squared dx. I got two choices now. You can integrate by substitution, or you can FOIL that, depending on who you are or how familiar you are with a FOIL. That is the easier way. Substitution may be easier for some of you. So this is 4 minus 4x plus x squared dx. All right, we'll go ahead and integrate this. We'll end up getting square root of 3 over 4. 4x minus 2x squared plus 1/3 x cubed from 0 to 2. Substitute in 2 and 0. 0 really just kind of cancels everything off with the x's. Get square root of 3 over 4. 4 times 2 is 8. 2 times 2 squared is 8. 1/3, 2 cubed is 8/3. That cancels. We got 8/3 times square root of 3 over 4, which is the 8 and the 4 reduced to 2. 2 square root of 3 over 3. All right? Feel free to check it. I'm going to check it based off of this one right here. All right? So as I use the graphing calculator, we'll go math 9, if you have the TI-84. From 0 to 2, 2 minus x squared with respect to x. I get 2.66667, which is 8/3. And I'll just multiply that by square root of 3 over 4. As you can see, I got 8/3 right there. Okay? So, in review, when you're doing volume with known cross sections, you need to know your area, whatever your cross sections are, and take your area times your width, which being infinitesimally small, you're going to go dx. You'll integrate it from the lower limit to the upper limit. And that is your volume with known cross sections.